Hello. Today I want to show you. I have a simple dataset, and I will show you how to uncover the relationship between these attributes. This is about motion, and it's the velocity has been recorded against time. So let's see what we can do with this simple dataset, right? Uh, this is a very simple dataset. I will share my screen now. You can see it. So the motion, uh, the velocity has been recorded against time, right? Velocity against time, right? Um, Let me set the working directory. Okay, this is the dataset, which is a very simple one comparing with my earlier data frames, right? So I will highlight a couple of important things using this analysis. Then I think this will be helpful when you deal with such a data frame. Um, so there are so many things we can do with this data frame, but yeah, I do not wish to talk about each of every due to limited time, right? So very important, very significant thing will be highlighted, right? Okay, so let me set the directory. Right. Forward slash. What is the name of the data frame? Let's call it V against T, right? Read dot CSV library reader is needed, right? Then read.csv. What's the name of the particular file? Velocity underscore type, right? Velocity underscore type dot csv, right? Okay. Um, just a simple summary. Let's take a look at the summary of the data frame. First of all, summary and the data structure as well. Right. Okay. Let it be run head of the data frame and the summary of the data frame and the data structure as well, right? Okay. So this is the head of the data frame. X. Surely this is just the row number, right? It is not needed for the analysis. T stands for the time and V stands for the velocity. These two fields are considered in this analysis, right? So simple summary is executed, right? these are means, then data structure, all these are integers, right? Okay, let's go forward, right? Okay, v underscore p. This is not needed. X is not needed, right? Just we can eliminate it from the system. V underscore t. Okay, let's see now. Yeah, that is eliminated, right? So even we have some more methods to eliminate that. So I use that this method, right? I use it in order to eliminate that particular unnecessary row. Sorry, the column, right? Then let's see couple of histogram of v underscore time of v, right, and box plot as well, v underscore t dollars, right? Okay, let's see. It's like this. It is skewed right. Skewed right. It looks like the density plot may be skewed right too much, and it seems like it is going to be given with an exponential distribution, which is the velocity, right? Velocity. If we try to put it fit it with the probability density function, it will be pretty close to an exponential distribution rather than a gamma function. Actually, gamma function I discussed in my earlier sessions as well. It is in between these two, uh, the normal distribution and the exponential, right? Once it is skewed, this gamma distribution is discussed. This is skewed too much, and it is pretty close to an exponential distribution, right? Okay, today I do not try to find out the distribution because in my very beginning sessions I have discussed all of them, right? So my desire is to uncover if there is something relationship. So with the help of this box plot, we can identify numerical outliers. This is free from numerical outliers. Right, okay. So what we could do further, we could plot it, right, using the default function, right? Default function v underscore d is to here, right? Let's see. Okay, now you can see it seems like there is a strong relationship. Let me find out the correlation coefficients as well. Correlation coefficient of between these two, right? Between these two. 0.89 linearity is explained strongly, but you can see it is not a linear relationship when we take a look at the scatter plot, right? it can be happen, right? It is pretty close to a linear one, considering this region, right? Considering this movement. So if it's all right, even we can uh, go through a linear distribution, but I try my best to find out the better one, right? Find out a better one rather than a linear distribution. So it seems like these 2 points are going to be outliers. They have violated this function. The rule behind that, it seems like there is a strategy, but these 2 points have violated it. They have broken the strategy. So I used to identify them, and this one is in between 0 and 20. So let's have a look at this velocity against time in between 0 and 20. First of all, let's identify it. Where is it? Where is it? It is pretty close to. It is less than even 10. Maybe this one. Maybe this guy, right? Maybe this guy. So the seventh row can be dropped, right? We have a couple of methods to do that, right? We have a couple of methods to do that. I'll show you it here, and I'm not going to run it, right? Because this has been used in my earlier sessions as well. So here I will use something for different new method, right? I will introduce that method to you. What you can do is just like my earlier sessions, we can omit the seventh row, and if you want to omit a couple of rows, what you can do, seventh row, and what is the other row? It should be identified. It's pretty close to 100, right? And even larger than 90. Actually, we are having only 100 observations, so it's not too hard to find it out manually like this. Otherwise, we have to subset it, then we can find it out, right? Approximately by checking the graph, we can notice it, right? So this is 95, it is corresponding to 95, so you can put here 95, 95, 95, which may work, right? So what we want to do is we want to let it be v underscore t, right? So I'll show you this is going to be going to work, right? It's going to work. You can see that 7 and 95 they are eliminated, right? They are eliminated. 95. There is no observation as 95 corresponding to time, right? There is one more method. There is one more method uh, that is, we can say, row v underscore t dollars velocity, or even you can say these. Yeah, let me run this first of all. To identify what are the velocities. Even you know velocities, and even you know times, right? You know velocity, this is something odd, so we want to eliminate that. We will exclude it, right? We will exclude it. Not only this one, but also we have one more observation like that. What is it? We underscore t dollars. We used to exclude that value as well. What is it? It is 83,932, right? 83,932. So this one. Right, okay. Now I will let it be equal with v underscore t further, right? Now, actually, I feel like it's a little bit difficult to type v underscore t, so I will make it vt, right? VT after eliminating these unwanted characters, right? What happened? Yeah, we have not contained these columns. These are for rows, right? Once we have excluded these particular rows, we have to mention what are the particular columns we need. So we need all columns, therefore I have put a blank there, right? So we can get all the columns excluding these rows. You can see they are omitted, right? They are omitted, right? Okay, now to make sure whether it's working properly or not, what you can do is just you can ask to plot VT, then VT speed, right? Okay, now, right, they were dropped, right? So now what I can do is I can find out the um, particular function. How do I find out the function? Actually, the most appropriate thing is to split this entire dataset into two parts. So I will use library CA2, CA tools will be used, right? CA tools will be used, then um, partitions, two parts split uh, split data frame, split into two parts, split dot data frame, data dot frame. Uh, let's say VT dollars T. Okay, by that split ratio is split the ratio split dot ratio. Sorry, there was an inconvenience. Sample dot split this one split split ratio equals we put 80% into the training, right? Then parts train will include what VT including parts with all the columns. VT does not include parts. Right, okay. Let's check whether it is split into two parts successfully. Dimensions of VT, dimensions of train, dimensions of test. Okay, let me set seed, right? Set dot seed with my lucky number always, right? Okay. Parts, what's wrong with it? Split. What's the unused argument? Split. Split ratio equals Okay, so you can see train includes 78, randomly 78 observations are taken into train and 20 observations are taken into test. And now we are ready for training the data frame, right? So I'll use linear, right? Linear regression. Actually, the requirement to be fulfilled by the response is to it should be a normal distribution, right? The response should be normally distributed in order to make it an effective regression. But here I feel like there must be a strategy according to this scatter plot. So I do not try to convert that into a normal distribution. Otherwise, we can transform it. But here, this I will keep doing it like this, right? Without doing any transformation, right? Okay. Now, ML, right? Linear regression model. V against time. Okay, time. Data equals train, right? Let me call this ML1, right? Let me call this ML1 and the summary of the model ML1, right? Okay, let's see. The adjusted R squared becomes 0.833. This is not bad, right? But I feel like rather than a linear distribution, there must be something. There must be something. So let me show you how to perform. This is linear regression model, right? So I want to reach up to a better output by performing polynomial regression, right? Okay, in order to perform a polynomial regression, I want to find out what would be the better degree of the polynomial function if there is, right? Okay, so I will use ggplot2 as usual, right? I think this was not shown earlier, right? To check how to plot what will tally with a higher efficient, right? With a higher efficient VT mapping aesthetic x equals time and y equals velocity. I need geom point. Then let's see, right? Okay. Geom point. I'm trying to find out which will be the geom smooth. Let me add geom smooth, right? First of all, then I will show you what is the difference between geom smooth and static smooth. In static smooth, we are allowed to find what is the best fitted one. So this is the best fitted one, but we want to find it out whatever the degree, right? So in order to finding out the degree, stat underscore smooth, okay, smooth, then method lim, right? Then formula in this. It's pretty similar to linear regression model, right? Then y is a polynomial, right? X, first of all, let's say it's a linear one, right? For a linear one, let's plot it for a linear one, right? But it's not fitted. Actually, this is what explained by this linear regression model, right? You can see this intersect is significantly evident. They are significantly evident, but you can see still there is a difference. Still there is a difference, right? It's not too much, but still there is a difference, right? So we will go for a better one, just like using, Taylor series, likewise, right? So this is a query format. Still, I feel like we can go further, right? We can go further. What about tree? What about tree? What about a cubic function, right? Yeah, it is fitted exactly, right? So it is fitted exactly. So hence I decide that this should be the a better one, right? This should be the better one. So I will actually this is VD, right? So let me change it with train, right? With train, because we are working with train. Let us say now when we prepare the model, let's see how it will be changed. Still, it is not changed. Says exactly it is fitted with the degree polynomial function. So let me change the linear regression model ML2. All these variables are significant. Only to actually we are having only two, right? So it's a very simple regression model, not a multilinear regression model, right? V against T, but poly, right? Poly. So what is it? Time, third degree, right? Rho equals, right? Okay. Data equals what is it? Train, right? Train. No, right. Okay. Summary of the newly trained model, right? Which is the polynomial regression, right? Now plot it, right? And then, right. Okay. Let's see. Right. Okay. Um, This is the linear regression. Now we got there are three. There are three components because it's a cubic one, right? So while it's a cubic one, this is the third one, t to the power 3. This is the corresponding coefficient, right? And this is the corresponding coefficient of what? Of t squared, right? And this is t, right? It's t, then right. Okay, and this is the intercept, right? Seems like this is negligible because actually when you have a look at this, it seems like this is insignificant. 40%, there is a chance of this much of chance to not explain the entire model, right? So we will omit that. According to the output, we can say, yeah, you can see that the R square is just 1 and the adjusted R square is 1. It's an amazing, it's the ideal stage, right? So p-value for the entire model is very good, right? Then uh, so using hypothesis test, depending on these probability values of these t values, you can say intercept is significantly evident and t to the power 3 coefficient of that and t squared coefficient, they are significantly evident. Only the coefficient of t will be rejected, right? According to these hypothesis test. So we can say t cubed minus 2p squared plus 1 equals v, right? Okay, so I am trying to compute the I try to compare here. Now you can see when we compare these two models, according to the earlier summary of the earlier model and the summary of the current one, you can see the difference, right? You can see the difference. This one, the R squared is just 0.833, and when I have shown you the plot, but here I have plot model, second model only, right? It doesn't matter, even you could plot the first model as well, right? And now you can see there is outlier. There are two outliers like this, residuals. There are a couple of outliers. This model, right? Same outliers. This is explaining the normality, right? Whether it's a normal distribution or not. Actually, we recommend normal output when we are talking about linear regression, right? So it's pretty close to a normal distribution. There are a couple of outliers as well. Right, standardized residuals, they are fitted with the ideal stage. Right, okay, likewise, right? So Cook's distance, right? Now we can accept this model, right? So I try to compare these two models using RMSE, root mean squared error, right? Root mean squared error. So what I can do in order to compare them, yeah. Okay, predict, right? Let's predict it based on the test. Predict and let's just call it P1, right? P1 predict what is the model? ML1 is the first model, right? And what is a new data set? New data equals test, right? Okay, test dollars p underscore true. Let's say we will do the same for the second model as well, right? New right. Now there was like new data, right? New data equals test, right? Okay. Now let's see the test testing set. Now we want to compute root mean square error. I think it's better to root mean square error. So let's check this. Okay, now you can see when we take a look at these two outputs, right? Predictions. When it is closer to this intercept, there is a large difference because of the inconsistency of the first model, right? So when we compare these values, even you can get an idea, right? Actually, this is fitted perfectly. This second prediction is fitted perfectly, right? But in order to prove this mathematically, I'll show you the computation. How do we compute root mean squared error, right? Function RMSE function. Let's make a function, right? Mean squared error. X minus mean of the test velocity surely this should be the difference between these two residuals, right? And then squared, we have to get the mean of that, right? We want to get the mean of this, then it's like this. Then root, square root, let's give the function, right? Hopefully, hope this may work fine properly, right? Okay, let's apply it to compute our MSE. Let's say it's 1, right? Our MSE inside parentheses, what is it? Test prediction 1, right? It's the observation, right? That's the observation. Then RMSE 2, or in the second model, RMSE test dollars prediction 2, right? Second prediction. Now let's paste, right? RMSE of ML1 is RMSE underscore 1, right? Let me copy this. ML2 is RMSE underscore 2, right? Okay, let's predict. Right, okay, you can see this is pretty small, and seems like there is no difference, but comparatively there is a difference this much, right? So though the r squared and the adjusted r squared value is a better value, but we cannot say by taking a look at the r squared value only, we cannot say it's a significantly that's a good model. When you have a look at this probability value of for the model, it's a better value, but statistically it's a better value, but there is a better model rather than this, so we could find it out using polynomial regression, right? So this is the importance of the polynomial regression. So using this example, I tried to show you the importance of studying these polynomial regressions as well. There are some more, because we know that in mathematics we are having so many functions. They can be polynomial functions, rational functions, transcendental functions, homogeneous functions. There are so many functions. So among all these, we have to uncover what is the particular strategy behind that, right? Okay, so I hope to figure out the function. I write it down as an expression, right? VT function. Let me call it VT function. Actually, we could add GG title, right? And xlab and ylab as well, but I did not try to just add it because of taking too much time. Just I wanted to pay attention on these computations and how do we handle these, right? Okay, when you do that, yes, you can add GG title, right? Okay, function. Mini function, I want a expression. What is the expression? Right. And now what's the t cube, t cube, t cube, t to the power 3 minus 2 times t squared, is it plus 1? Yeah, I think it is plus 1, right? Right, okay. This is VT function, right? VT fine, right? Okay, so I try to find out the acceleration, right? Using this. Next week, I will show you how to find out the displacement against time. You know mathematically what we want to do. In order to finding out the acceleration, we can find out the derivative. We can differentiate it. We can find out derivative. First derivative will give us the acceleration against time, right? Because the velocity is function of time there, right? Okay. So I'll use library dairy. This should be upper D, right? Okay. Now the function will work derivative or upper D, right? It doesn't matter, right? Okay. I want to find out the derivative of what? Of the expression VT function names by what? By T, right? Okay. Let's find it out. What happened? Unused argument. Is it this name? Names is used in labels, right? Let's run it. Right, okay. Now you can see yeah, this is derivative. Even you could do it manually, right? But if the expression is complicated a little bit, you could use you could depend on this function as well, right? Okay. Now what I'm trying to do is I try to find out I try to plot it, right? I try to plot it with the help of okay, time equals, let's build up a sequence. Here we are given from 1 to 100, right? From 1 to 100, length equal, length will be set as 100, right? Now this is my relationship between what? Acceleration. Let's say a of t, a underscore t, right? Okay, now data frame, let's call it a underscore t, no, at, right? Acceleration against time, right? Acceleration against time. Okay, now let's plot it. Let's plot it. Plot AT against time. AT A underscore T. Right. Okay. Let's see what about that. Okay, brilliant. It's a linear one as I wished because can it be a linear one? No, it's not a linear one. So 3 times t squared minus 2 times, actually this becomes 4 times, right? We will simplify it a little bit. There is no parentheses there. Then we ended up like that. Yeah, this may be a quadratic form. In quadratic form, the thing is while the curvature is not too much, right? Larger within 0 and 100 seems like a line, right? Seems like a line. Okay, maybe that, right? 600. Yeah. No, actually, it seems like a straight line. How it became a straight line? So, now it's problem with that. Let me start it with 0, right? When t equals 0, acceleration is 0 as well. When t equals, well, let me check this. Great. This data frame. Yeah, it's slightly different, right? It's slightly different, and it's yeah, and actually this should be changed, right? This should be changed because the data frame says. Let me change this. There should be an error if there is no particular field like that. I'm not sure it's why it occurred like that. There must be something, but it's like this. The we can rename that field, right? Right. Okay. Now it's fine, right? You can see the current format of that. So xlab can be add, right? Xlab can be add. Slab is time. Then uh, what about ylab? Ylab equals acceleration, right? Like that, even you could add title, right? Okay. So next time I will show you how to do definite and indefinite integrals using R programming, right? And all these things will be done even with the help of Python, right? After all these things, after only a couple of days, I hope to do everything using Python continuously, right? When I complete my latest project, right? Okay, thank you.